Okay, so welcome back to this machine learning with Python. It's the day 2 today. So just to remind you, here you have the web address of the workshop. So be sure to have a tab in your navigator with that address open. If you don't want to copy the address, you can just hit GitHub in Google, GitHub QCBCollaboratory, and normally it will be the first link here. So go here, go in Machine Learning Workshop 17, and go in the day 2 here, and you will have access to the slides over there and to material for some data set we'll see in a moment. So okay, so have a tab open here. Be sure to have open navigate the Anaconda navigator, so search on your on Windows, on Mac. If you're on Mac, just hit Command Space and type Anaconda navigator, or if in Windows, hit the start menu. We see Anaconda navigator. Open an instance of Jupyter. You should have this window open. Go into your document with the same directory as yesterday. Here, and you can create a new workshop with and you can change the title here. So here it will be Machine Learning Day 2, for example, and you can begin once again. Okay, so today what are we going to do? We are going to talk about classification and cross-validation. We'll learn how to assess the performance of a model, learn how to choose models from scikit-learn, and we'll do a proper cross-validating workflow. Okay. So yeah, basically is what I said. Open Jupyter, create a new notebook, and be sure to have import NumPy SMP, and to import matplotlib, matplotlib.pyplot as PLT. Okay, so you need to have those 2 lines in order for the rest of the workshop to work. Okay, so we'll work with today mainly with this data set. So this data set is just a synthetic data set. It means nothing in particular. It's a 2-dimensional for the feature. The features have 2 dimensions, x1 and x2, and we are going to work on that data set and try to make classifier. One that will recognize the red dots, and the other one the square blue dots here. Okay, so where is this data set available? This data set is available on the website here. So here you have the synthetic data set to practice classification. Click here to download it, and be sure to save it into the same directory as the one where there is the notebook currently running, so in this one. Okay, save it. Be sure to extract it, so because it's a zip file, so you need to, sorry, you cannot see what I'm doing here, so I'm just unzipping what we are doing, the workshop. So machine learning workshop, so here you have the zip file. Just extract the 2 data here. I'm extracting it, and normally I will have 2 files, like call machine learning ML, test dataset features, and label. Okay, so it's the same directory as the one where there is my notebook currently running here. Okay, so we have this data, and we can so this data these data are very simple. So if I open the dataset, the feature dataset, you can see it's very simple file. It's just 2 columns of numbers, just separated with a space here. So in fact, you can open the file with the usual Python way, use the open function, etc. But since this file is very simple, there is a numpad. You can use a function called load.txt, and it's able to read very simple file like this one when it's simple enough. So we are going to use that. So we are going to create an object called features origin, and we'll use the np.txt, load.txt, sorry, load.txt, and it will be called, and normally you can use the tab key. So you open the features. So I'll go to line here for you to see. So I'll remind you, if there is an open round bracket here that is not closed on the line, it will go to the next line as if there was no new line. And let's do the same thing for the labels. Labels, and the name is labels. Okay. Let's open those two things. Okay. So we are going to print the shape of each of them. Features origin dot shape, and the same thing here for the labels. Okay. So here there is 500 rows and 2 columns for the features, and the labels would just be 500 rows. So I remind you, the rows will correspond to the sample, and the column will correspond to the features. Here there is 2 features, x1 and x2, so only 2 features. Just reminding you that usually in a real data set you will have more features. Like the example of yesterday, we had like something like 30 features. So here just 2 features, it will be small enough so that we can plot it in a 2D space. But remind me, so we'll have very nice plots, but I will remind you that in real data sets it will be much harder to plot it in a nice way. So the example today is just for teaching reason. Okay. So the testing data set. So we are not going to make the same mistake as yesterday. As reminding you, yesterday we took a data set and we built a model on the whole data set. And after that, we happened to ask the question, are we overfitting? And since we use all the data set yesterday, we cannot assess if our model is overfitting or not. So here we are going to be careful about that, and we are going to split the dataset into one split for the testing dataset and the other one for the testing dataset. So yeah, it's a good way to do it prior doing anything, to split it into a learning dataset and testing dataset. The testing dataset will be our what we call our final proof. So it will do a final assessment of the performance of the model. If you want to have during you are constructing your model to have a rough idea of how your model is behaving, please do not use the testing dataset. It's not a good practice. The good practice, as we will see, is to use validating dataset, cross-validation, out-of-back accuracy, those kind of method. When you are constructing your model, you want to know what is the current, have an estimation of the current accuracy of your model. Use those methods, and at the very end, just to have your final proof, the thing that you will put on the article, what is the final accuracy, use the testing dataset. Okay. So yeah, the idea is this one. You have the original dataset here that you open, and we're going to divide it to the learning dataset and the testing dataset. We will use only this part to create a model, and this one will be used to assess the performance of the model at the very end. Sometimes I have the question, what is the proportion we need to use for the testing dataset rather than learning datasets? It depends. As a rule of thumb, it's good to use like 1/5 up to 1/3 of your original dataset to the testing dataset. Of course, if you don't have many samples, maybe you need to have you'll do your best, and maybe you use a little bit more for your learning data set because you don't have that much data. Is not optimal, but you do with what you have. Of course, if you have if you have a lot of features also, you need to have a learning data set which is representative to your whole data set. So it can be tempting to take a little bit more of the learning data set. Is a trade-off, of course. If you are just like 2 features and dozens of thousands of samples, then you can afford to take a very little testing data set, but usually we are not in that case. So as a rule of thumb, 1/3, 1/5 is something which is cool. Okay. So you can do it by hand, making the selection, but there is a method in a function in scikit-learn that can do it for you easily. So it will be in the sub-library of scikit-learn, which is model selection, and the function name is train test split. So we are going to import that, and as you can see, you have you can determine the test size and things like that as options. Okay, so let's use it. We are going to import in from scikit-learn dot model selection. Import trained test splits. Okay, and the syntax is the following. We are going to put here the features. So that will be the features of our training data set, and share the features of your testing. So features tests. So that will be for the training. That will be an array for the training, and that will be an array for the testing. I don't put the underscore train because I'm kind of a lazy programmer, because we are going to write features a lot of times in that workshop, but that is for the training, and this guy is for the testing. And do the same for the labels and labels tests. So those guys here are going to be, so I need to increase it a bit, train test splits, parentheses, I go to the line here, I can write it down. So here I put the features origin, I put the labels origin here, so that we are going to split, and then I could put the test size split, and here I'm going to just to take 1/5 of it, and basically it will be enough to say that, to do that. Just here I'm going to put something like shuffle, the option called shuffle. So it's not mandatory to put it, it's just that since by default, false. By default, the split is randomly done, so each row will be randomly select. In order to have the same result on my own computer as on yours, as when you're going to put some graph, if you want to have exactly the same result, just put shuffle to be false, so that the result will be exactly the same. It will be more accurate between your screen and mine, but of course if you don't want to put it, just don't put it. It won't be exactly the same results, since the split won't be exactly the same. It will be done randomly in another manner, but yeah. Okay, so let's do that. So if you have that, then you can then use have a look at the shape. So features origin.shape. So that was the shape of the original data set. It's 500 rows and 2 columns, as I told you. But if now we look at the training data set and the label data set, feature tests. Here, so here the features here is for the training dataset will have 400 rows, so 400 samples, and the testing will have 100 samples. Okay, and we will put this guy apart, and we will use it only at the very end. To assess the accuracy of our models. Okay. A good practice is not even have a look at the testing dataset. Just to put it aside, to be sure that you are not doing overfitting. sometimes even looking at the dataset can just insert a certain bias into your analysis. So it's good to not even look at it, just to put it aside and do it like that. Okay. Okay, so let's do it. So we're just going to have a look at the dataset, of course, just the training dataset, as I told you, and we are going to plot it. So let's just plot it. So plt.plot, and here we are going to take features, so that is all the features, and here I'm going to put like a string syntax here. Here I'm going to select only the rows for which the labels is equals to 0. Okay, so here labels equals to 0. So here I will select all the rows for which the labels equals to 0. Remind you that this is the syntax. Here it will be a boolean with an array of booleans with true and false, and since you use it as an index, it will select only the one for which it's true. And I will select only the first column, so it will be in column of index 0. So that is the x-axis, and the y-axis will be exactly the same thing with a 1. And here I'm going to plot it as blue circle, so B for blue and the O for circle. And I'm going to do the same thing for this one, the one with label 1 here. So I'm going to select the rows with index with the label 1, first column, second column, and here I'm going to plot it as red square, R for red and S for squared. Don't forget the plt.show here, and it'll work. Okay, I'm just going to do something just for me. You don't need to write that down, it's just to have a larger font size for you to better see my screen. So I think params font dot size something like 15. Okay. So if I do that once again, yeah, it's with a larger font size. Okay, so that's cool. You have your a plot of your data set. That is the x1, that is the x2, the 2 dimensions, and you have your dots. Okay, so it seems quite nice. Maybe we're going to try something. So let's try with what we said yesterday. We are going to build a tree, decision tree with scikit-learn. Okay. Okay, so let's build our tree, our decision tree here. Yesterday we see how to make a decision tree. It's in the sub-library tree here of scikit-learn, and we're going to import decision tree to classifier. Okay, so just so that is a screenshot of the documentation. So here you go on Google, you will hit scikit-learn tree, decision tree, yeah, something like that, and you hopefully, if you click here, you will have no, this one, yeah, this guy here. This guy here is going to be basically the screenshot of that. Here you can see that you have plenty of options that you can put here, like everything, and here you have the description of each of the parameter that you can use. So when you see an option and you're wondering what it is, just go here and click, and you will have information about the parameter. Okay, so we are going to use it. So let's first import it from scikit-learn.tree import decision tree classifier. We are going to create an object called CLF for classifier, which is just a decision tree classifier. We put all the options to be by default, and basically it's good. We have just for now created an object. We say to scikit-learn we are going to create a decision tree classifier. Of course, for now we did nothing, we didn't fit it. In the next instruction they're going to fit it. So I'm going to, for the classifier, I'm going to use the method that called fits with the features that should correspond to the labels. Okay. So now we're going to do like this little icon is doing, tune the model is going to tune itself to make it correspond to the data. So let's do it. Okay, so he plots some information, he fit the model with this criterion, this maximum depth, etc. Okay, cool. So yeah, so there is a method to know the accuracy of your model. Rather than comparing it like yesterday, you need to know like what is the proportion to the one which are correctly guessed rather than the one which are wrongly guessed. We can do it by hand, but there's a method for the classifier that can do it for you directly, which is called score here. So that's a method of classifier. It's only available, of course, if you already fit the model. And we are going to know the score for the features here and the labels here. Okay. We do not use for now feature test and label test because we just have an insight of what is the accuracy of your model. The feature test and the label test will be used at the very end with score, for instance, but only at the very end, in order to assume what is the accuracy of your model. For now, we're just testing a little bit things, so we don't use it. We keep it apart. Okay. Okay. So we had 1, meaning that 100% of features are correctly guessed. That is, of course, the best score we could opt for, and maybe it's too good to be true. Usually when you have 100% accuracy, you are very, very, very likely to do overfitting. So what do we need to check? We need to check that we are not overfitting. Okay. So maybe we can have a look at the tree that we had just built, right? We created a tree, maybe we can just overfitting it. Maybe we're just overfitting. And one way to have a guess about that is maybe to look at the tree to see what it's doing. So a way to visualize the tree is to use the graph viz interface. So we are going just to save what is the tree into a file using this file use the graph viz syntax. So to do that, we use the method scikit-learn.tree and import export tree. So export graph viz, which is a function which is going to write into a file what is the tree looks like. Export string graph viz, classifier, and here we'll put the name of the file in which we want to save it. So it will be graph decision tree dataset.dat, for instance. Let's do that. So here, if you go into your file explorer here, like Jupyter, you'll see a new file. Oh, I made a typo here. It's dataset here. So yeah, that's pretty much the same thing. I'm just going to remove this one. Sure. Okay, so let's open it to see what it is. Okay, so it's a text file. It's not really readable, but maybe we can just go here and select everything. Text. We are going to copy everything. Yeah, copy it, and we are going to paste it into a website that allows us to visualize what kind of tree it is. Okay, so open a new tab here, go on http://webgraphviz. Okay, so webgraphviz.com. Or here you can remove this guy here. So I'm going we can remove this guy, so the text editor is here, and just paste the content of the file you had just created, and click on generate graph. Okay. So, and below you'll see the graph. So the graph, in fact, the tree is very, very, very large, very, very, very long, right? So there is many steps, and maybe it's the way that a clue that you are overfitting. Okay, so that's the first clue. Another clue that we can look at it is the feature's importance. So what is the feature importance? It will say to Python, it will ask to scikit-learn, in order to make your model, how much did you use the first feature compared to the second feature? Since it looks like from the visualization that the two features are the same, would have the same importance to guess what is the two class. If we see something which is very different in feature importance, it will be an insight that that the model has been not well created. So here it's used with feature importance. Don't forget this underscore. So this underscore indicates that it's a convention used by the scikit-learn programmers to say it's something that is determined when you did the fit. If you didn't need the fit, then you don't have access to this guy here. So each time you see an attribute with an underscore at the end, it means that you need to do the fit before having access to that feature. Okay. So let's look at it, and here you can see that like 34% of the first feature represents 35%, around 35% of the importance in order to make the model, and the other one is like the two-thirds that remaining. So it means that in order to make my model, the second feature has much more importance than the first one. And since we look at this graphically at this model, we see that the two features seems to have around the same importance. So it's surprising that we have such not equilibrate features importance. Okay, we can do even better, to have an insight if we are overfitting. We can ask with the decision tree, what is the probability? That is, how much you ask the model, how much it is sure that is going to be a red square, a blue square, or no, a red square, or around a blue circle. So there is the decision tree can have a notion of probability. How much weight are you going to the first one or to the second one possibilities? And the prediction is that just is if it's above or below 50%. But we can have more insight into what is the prediction. Okay, so that is the probability. First of all, we can see what is the prediction. Sorry, we just first step, we do the prediction. So P1, what is the prediction for this dot here? For first feature is -1, the second feature is -1, and P2 is the first feature is -1, and the second feature is 4. And P dot array. Oh my god! So here I put 2 brackets in order to have the good shape for the feature. I'll remind you, like yesterday, it should be like the number of rows will correspond to the sample, and two columns. If you don't put the 2 brackets, then it should be just 2 rows. So it won't be the one that expects the shape that it expects scikit-learn. -1 for the first features, -1, and second features -1. And let's create P2 that is the same with the second features to be 4. And let's see what is the prediction. Print classifier dot predict of P1, and do the same thing for P2. Okay, so for the first point, it predicts that it's going to be a 0. So like it would be, I don't remember which one it is, but let's just mention that the blue circle, and this one will be the red square. Look at it. So yes, that's it. So that will be a blue circle, and that will be a red square. Okay, so just as I just said, you can have a better insight to know what is the probability that is given to for the P1 and P2. How much are you sure that it is going to be a blue circle, and how much are you sure here that it's going to be a red square? So let's do that. So here you just put it here, and the function is called predict proba. Okay, so the first row here, it says that it's 100% sure that it is a blue circle, and 0% sure that it is a red square. Here it says that it's 100% sure that it is a red square, and 0% chance that it is a blue circle. It has no hesitation at all. So maybe so the model seems to be very stubborn, right? It's 100% sure of what it's doing. And of course, when you have such a model, it's a huge insight that maybe something is wrong. It should not be 100% sure of what it's doing, right? So it's a new insight that you might do another fitting. Okay, so we are going to draw the decision boundary. So what I mean by that, I will plot to plot a kind of heat map, and when it will be red, it means that the model will predict a class 1, and when it will be blue, it will mean that in that position, with that first feature and the second feature, the model will predict a class 0. Okay, so how do we do that? In fact, we are going to make. So we are going to make a grid with plenty of dots. So the grid step will be called delta here. So the smaller the delta, the more thinner will be the grid. And for each dot of the grid, here you have the x-axis and the y-axis, and we'll ask to the model, what do you predict for that particular point? And basically we'll do like that. So real kind of technical, I will do step by step explaining how do we do that. So the first thing you need to do is to create here two vector here, x, small x, and x will represent all the abscissa of the points, and y will represent all the ordinates of the points. Okay, so if I access to the ith element of x, it means that it will be the abscissa of the eth point, and the same thing for y here. And then we are going using the method called mesh grid, two matrices or 2D arrays to be precise. One will represent all the abscissa of the points, and here this one will represent all the ordinates of the points. You can remark that those two arrays have the same shape here. And for example, if I look at this one, the element at position ij, it represents the x-axis of the point. And if I look at the same element, so that's capital Y. In capital Y, it will give me the y-axis of the grid. Okay, so this array here, just copy-paste plenty of times of this array vertically. And this guy here is the copy-paste of the small x vector, but horizontally. So it's what we'll have. If you want to access to the abscissa of the point, you look at the capital X matrix and the capital Y matrix if you want the ordinate. Then we'll take this matrix here, and we will what we call ravel them, that is to flap them if you want. So the first line here will be this guy here, and the second line here will continue here, and you go until the end. So it will just give you one vector, one array with all the x of the point, the abscissa of the points, and you do the same thing for the large y. So that will be the first line here, will be copy paste here, etc. So if you look at the first element of this guy, it will be the x-axis of this guy, and the first element of this guy will be y-axis of this guy, and you will continue as you go here. You'll go through all the points of your mesh. Then you will look at what do you'll take your model and you ask what do you predict for that point, for the point with that x-axis, the x coordinate and that y coordinates, it predicts to be a blue, etc. So you will have a vector for all the points blue and red, and then you will use something we will call reshape in order to reshape it in the same shape as the large Y and the capital Y and capital X and capital Y, in order to have the figure to plot at the end. So I explain it step by step what we are doing, and we are doing it here in the following slide. Okay, so let's see here. So here we are going to create delta. So as I remind you, delta is how thin will be the grid. Okay, so I use a grid of 0.5, and I will use x. So the x will be just the x-axis, lowercase x for now. np.arrange, so it will be a range from -2 up to 5. I remind you that arrange don't include the last element. So a way to just hack in order to include the last element is just to use something just slightly higher than 5 in order to have it. So it will be 0.5, like, or just 2.0. And here I put the step would be delta. I do the same thing for y. Here I choose to do exactly the same, but it can be different if your first axis and the second axis, the first feature and the second feature are not exactly centered around the same points. And we are going to create our capital X and capital Y. I remind you, it's the matrices that is a copy-paste of all the X and copy-paste of all the Y. So capital X, capital Y just be the results of a function called mesh grid, that is part of NumPy. Mesh grid. Here you just put X and Y. So X and Y. So let's have a look at what it's doing. So X is indeed to be an array with plenty, the line copy paste plenty of times, and Y the same thing, but just the columns. Okay, so we have our mesh grid, and Z is going to be our results. So it will be the prediction of your classifier, clf.predict. Okay. So here, this guy here will be just the X 2D array flattened. So x.travel will be just you flat it in order to make one single column, and this guy here will be y.travel to make it a single column. What you need also is to glue those two arrays here into one single array with just two columns and as many rows as there is points. So you have plenty of ways to doing that in NumPy. The more convenient way, even if it's quite strange, is to use something in NumPy called C_, and here you put square brackets and the two vector that you want to glue together. It's a very strange syntax. I don't really know why they use this one, but it's very convenient since we'll do a lot of that in scikit-learn. Typically want to glue array together that represent different features, and you want to glue them together in order to have a 2D array, and the simplest way to do this is using that syntax. So I'm going to use it, np.c_, and put here a square bracket. It's not a round bracket, it's a square bracket, very strange. And here you put the first vector, which will be x.radle and y.radle. Okay, so that will be the prediction. So basically, we have created those two vectors here. We glue them together into one single 2D array with two columns with the C__ method. And we have created this guy here, and we just need to reshape it. So we'll use reshape. So Z is going to be z.reshape, and here with this function reshape with method, sorry, we need to put the shape, and in fact it's the same as, for example, x. Okay, and we are going to plot that using pyplot. So in fact we use the function called contour_f. And here you put x, y, z. And here I'm just going to, so the color by default are not the one I want, so I'm just going to specify what color you use for when it's 1 and when it's 0 in order to correspond to my example with red and blue. So just is what I'm doing, writing here, cmap the plt.getCmap, and here I got jets, so it will give me a code of color where 0 will correspond to blue and 1 will correspond to red. You can go on the documentation, see plenty of other codes of color if you want to use others. And don't forget to the plt.show. Okay, let's do that. Oh, I make it's Ravel here. Okay, so imploding means something, but as you can see, yeah, so it's a little different because the decision tree is randomly done, but it's more or less representative. You can see that the dot here is not very precise. It's because the delta is very large. So we are going to decrease this delta in order to have thinner representation of the thing. So you just go here, you Control A, Command A to select everything, and you are going to plot it, for example, here. Command V, and you are going to decrease the delta. Let's take a delta of 0.01. Okay, so it's much more precise here, and as you can see, you have plenty of small lines, and clearly those lines are sign of overfitting. You want to access to specific dots in order. I mean, it made a tree so much complicated that you want to access to specific dots using all that cases. So note that here it's straightforward where we are overfitting, because we can plot it in a two-dimensional space because we just have 2 features. I remind you that usually you have like 30 or so features. It's not that obvious that you are overfitting. Okay. So yeah, basically, if you look at your data sets, maybe in order to access to this guy here, you made this small line here and things like that. So you want to access to all the elements whatsoever, in order to be sure to select every dots, and clearly it's a sign of overfitting. Okay, so basically, maybe we will decrease a little bit the maximum depth in order to have a smaller depth for the tree, and let's take a maximum depth of 5. So we're going to create a new classifier. It's going to be a decision tree classifier, and here I'm adding the maximum depth. That is going to be 5. Okay, clf.fit, and here to be the features, the labels. I'm going to print the score. Okay, and I'm going to export graph with clf, and here it will be graph this dataset 2. Okay. Okay, so this guy here seems a little bit better. Since you have reduced accuracy, so it's not that sure what it's doing. You have some uncertainty, so it's already a sign that maybe better for the overfitting. Maybe you are underfitting because maybe 5 is not large enough, but it's already, at least it's not overfitting. So we have saved this the new graph in a new data set here. So if you come back here and you go in that guy here, you will see a new tree. So just by the length of the file, you can see it's much smaller than the previous one. Just copy everything, go in the graph viz, .com, that's it. No, it's not this one, sorry. I just come back to have the correct. Wait, here it is. WebGraphics, sorry, I forgot the web there. WebGraphics.com, yeah. So I'll come back here, I paste it, I generate the graph, and it's much smaller, right? Okay. And let's plot it also to see what how it looks like. So you just have to make a big copy and paste it here. Okay, so that seems at least more less sure of itself it makes some prediction which seems to be a little bit better. Okay, at least with less overfitting. Maybe there's underfitting, but we'll see. Okay, so now we are going to create a random forest like yesterday, as I explained to you. We have created a decision tree, which is not a very good predictor, right? It does not seem to be a very nice prediction of the data. But we are going to create a random forest that will just basically create plenty of different decision trees in order to create maybe a more precise and not that sensitive to the fitting procedure. Okay, so the way we do it, so yesterday what I did is I give to everybody of you a data set with only two out of 3 features. I mean, the more natural way, the simplest way to do it is to do it a little bit differently. Is just to give to each of the data set just a subsampling of all the data sets. So here you have your data sets, and here you are going to select, you're going to make a small subsampling, just take some of them and create a tree with that. Here we're going to take another subsampling with another tree with that, etc. So you're going to do it plenty of times, and you will have plenty of classifiers, small trees. And what will you do is to make new prediction, you will ask the prediction for all these trees, and you will take the majority and see what is the majority giving to you. Okay, the global answer. Okay. So of course you can do it by hand, go through all the points of your data set and select them in order to make them in plenty of steps, but you can do it directly with functions of scikit-learn as well, and it will do it for you with that function. So the random forests are in the sub library called ensemble. Ensemble is just a way to say we are going to take a simple model and make many of them, and going to take the average. So it's the kind of ensemble, and here we're going to make a forest. Okay, so we can see plenty of interesting parameters like the number of symmetry, the number of times you are going to make the tree, number tree. The criterion is exactly the same thing as in decision tree. Here's Gini by default. Of course, since you are going to create plenty of trees, you have all the options of the trees, like the maximum features and maximum depth. I think it's somewhere here. As you have the same, you can make it in the random forest. Okay. Just something. So you always want to know if you are overfitting, and you want to have some heuristics in order to estimate the performance of your model. Of course, you have some testing data set you put aside, but it's not a good thing to look at them since you are going to build your models. It's better to use them at the very end when you think you have a good model and you want to assess definitely the performance of your model. So in order to, during the process, to know what is the accuracy of your model, is you have something in the random forest that allow you to estimate the performance of the model using what we call out of bag score. So when you make one tree, you have used some of the data and you have plenty of others. So you can assess the performance of that particular tree using the other data. So it's what will you do? It will assess the performance, and it will aggregate for all the different trees, the different performance, in order to give you an estimate to make the tree. Okay, so we're going to use this guy here, and you need to put Boolean bootstrap to be true in order that to work. Okay. Okay. So let's do it. From scikit-learn .ensemble imports random forest classifier. Okay, a classifier. Random forest classifier. Number of estimators is going to be 50. The maximum depth. be 5, and you need to put out of bag score to be true. Classifier.fit, the features with the labels, and we are going to print the out of bag score. So I remind you that since there is an underscore here, it means that it's something that is going to be computed by the classifier once it makes the fits. So if I put print clf.ob score before doing the fit, it will give me an error. So it does the fit and compute this guy here, and you can do it. Okay, so 94%. Cool. Let's see what is the accuracy for the whole data set. Okay, classifier dot score, features, labels, and I think that's it. Yeah, I can print it, make a print like in the slides. Okay, 97%. Of course, this guy here is more precise because it's less sensitive to overfitting. Since here you use all those data sets in order to build your model and you test it on it, you might say that you are over-exaggerating this guy, you're over-exaggerating your real performance. This guy here will be more precise. And you can look at the features importance. Oh, sorry. Tick. Yeah. Here. So it's much more balanced, like 45, 55. Okay? And let's plot it. So just go back here, go big copy, big paste, restart. Okay. So this means it seems to be more or less what you wanted here. So of course you have some dots here, but globally it seems to be a model that will be less sensitive to to overfitting, right? Or underfitting, in fact. Okay. Okay, so there's another type of ensemble method which is called ADA boosting. So I don't go too much into the detail, just have a word about it because it's sometimes used. The idea is to have an initial tree and that fit pretty much the data, and then to look at specific data from which has been misclassified, and redo a tree on top of that take particular attention to those misclassified information. So if I take an example here, you have a data set here, you built your first tree, which is very simple, etc. And from this tree, you look at the one which has been misclassified. So those guy has been misclassified, and you put an extra weight to those points here, and you build a new tree that will take especially into account those data sets, so kind of an adaptation. And so you built your tree once again, so a little bit more advanced. So of course there is something, there's a rate at which you take into account these misclassified points. Then you look at the points which have been misclassified, and you try to make a new tree that take into account those points which has been misclassified. So basically there is a method into a scikit-learn, ensemble method. Pretty much you have parameters here. The one which is interesting is the learning rate. Of course, if the learning rate is too high, maybe you will go too much into the small details of misclassified one, and it will be overfitting. If it's too low, then it will converge too slowly. So it's up to you. You can have a look at this one, trying to use it on some data sets. Okay. So just to tell you, as you see, each time we applied a model, it was always the same kind of way. First from scikit-learn dot to the sub-library, import the classifier. Then I'm going to create an object of classifier with all the parameters. Then I'm going to fit the classifier with the features according to the label. It prints me information about how it did it, made the fitting with all the parameters here. You can have the accuracy score using the model score, features and labels, etc. And yeah, so basically it's always the same kind of thing that you will see later. It's always import from scikit-learn sublibrary, import that, create the classifier, fitting it, having the score. It's always the same kind of recipe. Okay. Okay, so the support machine vectors. So as you can see with the trees, it makes some very sharp decision, and so very vertical decision to construct the tree. Maybe in some applications, so it can work pretty well, especially if you do like random forest and out of bag first classifier. The random forests are very good, but maybe you want to have something that is more smooth, that will take the contour of something more smooth classifier. And there is something called support machine vectors, which are very nicely done and will give you some results which are very smooth. You see that we don't have these very strange limits here. It will be much more smooth. Okay. So what is the support machine vector? I won't go too much into the detail as always, but I'll just give you an insight at what it's doing. So basically what we'll try to do is, if I take my example here of the data set, it'll try to find the best function, smooth function, in order to turn around all the data sets, and we'll try to make a function as smooth as possible, and it's not going to turn too sharply, and try to contain the maximum of dots here. Okay, so it's the kind of the idea. So yeah, it's basically what I do here. Here it created a function here and trying to maximize what we call the margin, in which it does not want to have too much dots inside, and especially not dot misclassified here. So the computer tried to find the best of this function. The function, in fact, is what we call a kernel function. So just I will not go too much into details, but just to say that there is, you can imagine a small Gaussian around this dot here, and try to have the minimum as dot inside the peak of the Gaussian. I will speak about the Gaussian later because the once parameter was due to that. So you can imagine plenty of Gaussian centered around the center, and you have a margin, which is the largeness, the width of the Gaussian. And you try to have to minimize the number of dots into that function and under the bell, and try to classify it best. Okay, so you can have, as always, there is a function in scikit-learn. You can go here, and you will have in the SVM is support vector machines, and SVC is support vector classifier. Okay. You have parameters, and you have two parameters, which is very interesting, which are C and gamma. By default, gamma is auto. It's just an heuristic, and we are going to change it to be something particular. The heuristic is something like 1 over the number of features, but it's just an heuristic, and usually it's not working that well, so we'll change it. So what is C and what is gamma? So the penalty parameter C is how much do I put some penalty to misclassified data. So here, this guy here would be misclassified. What is the penalty? So we try, in fact, the algorithm try to minimize one score function, and the score function have a penalty for the misclassified data, and how much penalty you give to that. Okay. So we'll try its best to minimize the number of misclassified, and the intensity at which you want to minimize it will be the parameter C. The other parameter, which is the gamma, and it indicates how much the SVM can turn. So in fact, it's this. Before I say about the kernel function, which is a Gaussian, is 1 over the parameter. So it's the other way around we want you can imagine. So if gamma is very small, it means that you can have very small standard deviation. So we'll tend to turn it will have very large standard deviation, and so it will tend to turn very small, very slowly, right? If gamma is much higher than 1, then the standard deviation is very small, right, and can turn very quickly. So of course, if gamma is very large, then you will tend to overfit, of course, and if it's very small, it will tend to underfit. Of course, those two parameters, C and gamma, will just like sometimes be go in a opposite direction. If you have a gamma very small and very high penalty C, it does not know very what to do, so just like kind of minimize a very high function with a addition multiply or addition with the sum with a very high function to try it best, but it give you the insight of what the algorithm is doing when you change gamma and when you change C. Okay, so we're going to do that. We are going to import the classifier, right? So from scikit-learn dot support vector machine import. So it will mean you need to use the uppercase SVC classifier SVC classifier dot fit the features with the labels. Okay, and we are going to print the classifier dot score with the features and the labels. Let's go. 96% of accuracy, quite good. Yeah. Okay, but here we use the default gamma. Maybe we want to use a specific gamma. So the default gamma is 1 over the features, something like that. It's just an heuristic. We are going to use another gamma, like much larger gamma. So here gamma is going to be 10,000. Okay. Here it's 1. So maybe here we are doing overfitting. Let's go inside into that. Okay. So let's plot it. So rather than copy pasting each time the way to plot it, let's just make a function that we'll call in order to plot the contours. So we'll go back here, we'll take this guy here, we'll paste it here, and we're going to create a function with that. So the function, I remind you that the function is introduced by the keyword called def. I'm going to call it plot contours, and this function is going to have several parameters. Forget about this fig name, I forgot to remove it, so we don't put fig name here, just classifier and delta. So CLF, which will be the classifier, and delta, and here I can put a default value which is 00.1. Okay, so I will remove it here. I put column, and remind you in Python, if you have a column, it means you are going to define your function. The way Python knows where starts the definition and where it ends is with the indentation. So all those guys here needs to be indented. You can either go to the very beginning and go hit tab, to indent line by line, but since we are in Jupyter, you can do it much more convenient way. Just select all the lines you want to indent. You don't even have to select up to here, and hit the tab key, and we'll indent everything by itself. Okay, so basically it's more or less the same thing. Just add here, just to be nicer, the X label and Y label. So plt.x label, it will be x1, x2. Okay, so be careful here for people who are not familiar with Python. All those guys here needs to have the same indentation, otherwise it won't work. Okay, so let's select that. Here it does pretty much nothing because it just had defined a function, but we are going to use this function right away. So let's use it for different classifiers. So let's just use CLF dot here SVC. Okay, the classifier would be SVC, and the parameters here is going to be C100 1000 and gamma to be 100. Okay, let's try that and let's plot it. Plot, oh, sorry. So CLF dot predict, sorry, to fit features with labels. Okay, and we're going to plot controls with CLF here, and we're going to use the default delta. So that we'll use it as the default one here. Let's do that. It takes a while. Don't worry. It takes a lot of time. Okay, so this does it. Okay, so here, as you can see, maybe your gamma is too large because it makes some sharp turn around small data. So here, basically, you should have a dot and just make circles around here. So maybe we can reduce gamma. So here's what I'm doing. Try to do it like in log scale. So don't hesitate to divide by 10 or 100. And let's do it again. It takes a while. That's normal here. Okay, that's a little bit better, but it's not that bad. So maybe here C is too large. Try to change it to see what's happening. Okay. So when I put 0.1, it means 0.1 is what it is. Okay, that seems a little bit much better from what we would expect, like C to be 0.1 and gamma to be 1. That's okay. More or less we played with the model and try to find something which is not overfitting. Okay. Okay, so we'll learn how to fit the hyperparameters. What is hyperparameter? So basically you will use them without knowing them. Hyperparameter is all the parameters that you are putting in order to create your model. When we use C, when we used gamma, all those guys here were hyperparameters. In decision tree classifier, you have the maximum depth, which is an hyperparameter. So what we do so far is just try to guess a little bit what kind of hyperparameter will be the best. Sometimes it can be a good method just to try them and see if it works. Maybe we can do a way to systemize the way to do that. And also something to be very careful about, maybe you can be tempted, and it's very tempting, and several times I want to do it and I need to remember myself that is not the good way to practice, is to look at your testing data set. You test it and say, oh, that's not good. Well, my model is not behaving the way I wanted it to behave. Maybe if I change a little bit the hyperparameter to make it better correspond to my testing data set. By doing so, you risk to overfit your model to the data that are used only to assess the final performance of your model. And in that way, you will overfit your model on your testing dataset by just tuning your hyperparameter. So it's not a good way to do so, and you need to tune your hyperparameter. It's also called metaparameters sometimes, so don't be surprised if you see the other way to describe them. And the good way to do so is a little bit different. You need just to use a training dataset in order to have an estimation of your of the good hyperparameter to use. And then at the very end, when you have your model that you think is very good, then you test with your testing dataset in order to have the good estimation of the perfect estimation of your, the best estimation of the performance of the model that you can have, and biased estimation at least. Okay, so the way to do that, one way to do that, how to know that you are not overfitting with your hyperparameter, is to subdivide your model in 3 datasets rather than just 2, in the training and the validation and the testing. So basically is what to do that. Be careful, the testing dataset is not the same thing as validation dataset. The testing dataset is the dataset that I put apart at the very beginning of this workshop day, of this day. It's just to assess the final performance of your model, and validation is just a way to assess during the run what is your performance of your model. So the way we do that, before we just do the learning dataset and the testing dataset, and here you are going to subdivide your learning dataset into the training dataset and the validation dataset. Okay, how do we do that? So basically we do that using the same function at the very beginning of the workshop of this day, which was train test split, is what we are going to do here. So normally it should be already available, you don't need to import it again, but just to be sure I'm going to import it again, it won't change anything. From scikit-learn dot model selection, import train test split, and here I'm going to create the features that are the training dataset, xtrain, wait, no, it does not do it, x valid, and sorry, y, so that will be the labels for the training and the labels for the validation. Train test split, I go to the line here. So what are we going to split? We are going to split the features. So features are from the learning dataset, so it does not contain the testing dataset. And the same thing for labels. The test size, I'm going to take test size, yeah, 0.33. It means that it's 33%. And shuffle is going to be true, to be false, just so that you will tend to have the same result as I do, because otherwise it shuffles the data set and select them one after the other. Here we would just take like 66% to the first one to be the training data set and the rest to be the testing data set, the validation data set, sorry. Here are just going to be false, so you have the same result as I do. But of course it's not mandatory if you want to have really shuffled data. Also sometimes the data are sorted, like in the first features can happen, so a way to shuffle it is to select them really randomly. Okay, let's plot the shape, print x train dot shape, and here the x valid shape. So here you have your data. I have 268 rows and 132 for the validation dataset. Okay, so we're going to do that and assess the performance of our model while we are going to search for the good gammas. Okay, so we are going to put plenty of different gammas in the like of log scale and try to know how the training datasets, how the prediction of the validation dataset is performing when we're training on this one. Okay, so the set of gammas, I'm going to have, it will need to be an array here. I'm going to begin from 003, here will be 0.01, here will be 0.3, here will be 0.1, 0.3, 1, 3, 10, 30, 100, 300. I'll just go to the line so you can see everything here. Right, 3, 1, 1, 3, 1, 3, right, 10, 30, okay. And I'm going to put all the accuracies, it will be just an empty list that will fill in the for loop. For gamma in set of gammas, CLF is equal to SVC, so it will be classifier. I will just put C to be 1 for now. I'm just going to use the best gamma I can, and gamma is going to be gamma. Okay, so we'll go through all the gammas of this array here, and we'll create a classifier with the corresponding gamma here. I'm going to fit it, classifier.fit, take x train, y train, no, sorry, yeah, that's it. And here I'm going to save the accuracies. We're going to add what is the accuracy of this particular classifier, what is the score on the validation dataset and not on the training dataset. Classifier.score with x valid, y valid. Okay, so once the for loop is finished, I'm going to plot here set of gammas. Okay, so that will be the x-axis and the y-axis will be accuracies. Okay, we are going to put an x label because we want to have a nice plot. Label is going to be accuracy up, and so that will be the y label, and the x label is going to be gamma. So you can use you can use the LaTeX syntax in order to write some equations using matplotlib. The only thing is, the drawback is, if you use a backslash, sometimes like backslash n means new line, backslash t means a tab. So, and since the LaTeX is using a lot of backslash something, maybe Python won't interpret it the good way. So the way to do that is just to put a small r at the very beginning, before the beginning of the string. Here, don't put any space here, so just at the beginning. It means that each time you see a backslash something, it really means a backslash. It does not mean something else. And that r for row, okay, that's a row string. And here I can put gamma. So each time you put some LaTeX syntax, put a r to be sure that it will work, otherwise you will have very strange result or very strange error. Okay. Here you can remark that I use a set of gamma which is in log scale, and you can specify with matplotlib that you want one scale to be a log. So it's set, x scale, and here you just put a small string with log, meaning that I want the x scale to be in log scale. Don't forget the show. Okay, here. Okay, it takes a while. Okay, well, just see. So you don't need to write that down. It's just going to increase the font size. Font size. Okay, I need to plot it again. Okay, so you see better. Okay, so you can see as you change gamma at the very beginning, the performance, the accuracy is very small. It increases. So here it seems to be around that part here, it seems to be optimal, and then you are increasing too much, then it's decreasing again. So basically here, this part here will be the overfitting, this part here will be the underfitting, and that around here to be the optimal solution. Here, the reason why we have a decreasing here is because we estimated the validation using the x valid and y valid, right? If we use the x train and y train, we can see what would have happened. So rather than estimating the score using the training, the validation dataset with the training dataset, here's what we have. We will have an increasing always. It will be always better, and we won't see the other fitting. Okay, so it's always good to have that. So here I'm going to put valid. Okay. 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 So here we use like the training, validation, testing dataset, and what we'll use now is something a little bit more precise, even more precise, is what we will call cross validation. And you see just a small change with that result. So yeah, it's what we had before, the train, validate, test dataset, and here we can do something a little bit different. We can go through different step here, and we're going to subdivide our training data set into four, the learning data set into 4 or more subdivision, and we'll make a first model using that guys as the training and that guy as the validating. Then we'll use this guy as the training and this guy as the validating, etc. And you will assess the performance for each of those, this one, and this one, and we'll have an even more precise estimation of the accuracy of your model, since you use different subsets to create your model and to assess the performance, so it will be even more precise. Okay. So the way you can do that is using the k-fold train trace, and it will give you basically that, and we'll go through a for loop to do everything. So is what I'm doing here. So from scikit-learn dot model selection, import k-fold, so it's a capital F, a K and F. Okay, so it will be a kf, k-fold, the number of splits and splits, and splits 4. So it will create me a k-fold object. What is a k-fold object? So basically we'll use it in the for loop. For train index. So it gives you the indexes, so that is to say the rows, like all the rows from from the 0th up to the 25, for example, and all the rows from the 25 up to the end, something like that. So it will be the number of the rows, the index of the rows. Valid index in kf dot splits features. Okay, so you go through all the features. Oh, sorry, it's not an equal here, it's in. So the first step will be the first training index, then valid index, etc. So here I'm going to say use the same syntax as before, the same name as before. Xtrain is going to be the features with the corresponding rows, so it will be the train index here. The same thing for the validation here. Valid, and the same thing for the labels here, and basically just need to do that, labels, and right, I'm not mistaken, seems to be correct. Okay, then we're going to basically, in fact, just going to copy paste this guy here. So we're going to create a classifier with constraints c equal to 1 and gamma 0.5. We're going to fit it, and we are going to print the score with the x valid, as always. Let's go. Okay, basically it gives you that. So what does it mean? It means that for the first one it's like 92% of accuracy, this one 95, etc. So you can like take the mean, and the mean will give you the more precise estimation of the accuracy of your model. Okay, so for each step, etc., it does it. So take the mean, and we'll have a more precise one. Like the first one, if I do it like if you just do it with the only this guy here, maybe you end up with the 98% of accuracy. Maybe it was just by chance because you have some data that correspond to what you wanted. If you do that, you have more precise estimation of the accuracy. So we are going to learn how to evaluate the performance of our classifier. Here it's to answer the question that I gave you yesterday. What if you have a model where like cancer cells and benign cells, but in your samples you have like 98% of your cells which are benign. how do you assess the performance of your model? Because if you use just the accuracy, then a model that will always predict that the cells are normal cells will have 98% of accuracy, which is very, very good, as it seems, but it will completely miss all the cells which are cancer cells. Okay, so that's a problem. In order to assess that problem, I'm going to explain you how to do it, use other way than the accuracy in order to assess the performance of your classifier. So that works only when you have like a yes or no classifier, just you want to label your classifier, which is most of the time like that. And what you want to estimate, which is the true label, the true labels, is what we call the ground truth. And of course, the predicted truth is the one we predicted with your model. And since you have just two classes, class 1, class 0, true, false, cancer, benign, things like that, you can have this table here. So those guys here are the ones which are indeed like cancer cells and that have been predicted to be cancer cells, so cool. The false negative is the one which were predicted to be negative, and in fact they should have predicted to be positive, so it's false negative. The other way around here, a false positive is the one which has been predicted to be positive and should have been negative, and the true negative is only the one which were negative and has been predicted to be negative. Depending on one you want in your model, what you want to predict. So basically you want to detect the cancer cells, so the cancer cells will be the true positive. You want to better estimate the true positive. You don't care too much if you have a little bit to have false positives here. Maybe if you have some cells which are predicted to be cancer and they are not, you don't care that much as far as you have all of them. Okay. So what kind of model you can use? So what we use so far is the accuracy, which is all the one who have been correctly predicted divided by the total. So that is the true positive plus the true negative is the one which has been correctly predicted divided by the total. So you can, it's what we use by default using the score function. When we use like score here is what we did. We use that accuracy here. Of course, since you are in scikit-learn, you always have functions for that. So you can use like scikit-learn.metric to access to a function which is the accuracy score, which is do exactly the same thing. If you use that function with those here, it will work. It will do the same thing. So yeah, basically is what I said. Maybe the accuracy is not the best tool to use it in the model where you have very few of them which are cancer cells. Then a classifier that always predict that is a benign cell, then will have an accuracy of 99% of accuracy, and still is very bad model. So you have other ways, other metrics that can help you to know if you are doing things right. You have the precision and the recall. So since I'm always kind of mixing everything up, you can see that's a Wikipedia copy-paste from the page schema. So you have the precision, it will be the true positive divided, so I can, yeah, I will do that. Yeah. It's the true positive here divided by the total of the one which has been that has been correctly predicted, and it's if you want to increase the precision, then you will answer to the question how many selected items are relevant. So relevant item would be, is it a cancer cell? That is the relevant item. So how many of them are relevant? And you have the recall, which is a little bit different, which is how many of true positive divided by the total number of relevant elements. So how many of them did you catch? How many relevant element did you catch with the model? So maybe in the context of benign cells, cancer versus benign cell, you want to have a better recall. You want to select as the maximum as you can of cancer cells. The precision, like the example when you want to increase the precision, would be like save the videos in YouTube. You want to have videos which are safe for kids. maybe you want to have a better precision, because when you will increase the precision, you will ensure that all the video that you just present to the kids are safe for them. Maybe you will have some videos that would have been safe for kids that you misclassified, but at least the one you are presenting are much more likely to be classified. So it's a kind of the two examples that you want to have. Okay, that's the precision and the recall, and you can mix it. Okay, yeah, you can have access to them in the matrix. So you have the sublibrary matrix, precision score, recall score, and you can use it just like the score function. Yeah, sorry, let's go back here. So if you want to access to them, it will be, you can use like the score function with the same syntax here, and with precision score and recall score important from matrix. You can mix the two together in what we call F beta index. So that's the definition here, and you have a parameter beta. If you are beta lower than that, than 1, it will a little bit favor precision. If it's higher than 1, it will a little bit favor recall. Of course, when you look at just one indexes here, it does not give you that much information. Just if you just look at precision and you have a precision of 100%, maybe it's a model that say that all the videos are unsafe for kids. So you'll be sure, 100% sure that all the video that you will show to the kids, which is to say none of them, will be safe. If you pay too much attention to the recall, then you will classify all the cells to be cancer cells. Okay, so it's always good to have to look at the two together, or you can have a look at the F beta that tends to glue them together into one single matrix in order to have a balance between the two performance. And very often F1, so for beta it's equals to 1. It's what is used usually in medical application, and tends to favor the two. If you want a little bit of precision, a bit of recall, depending on your context, maybe you can use another beta if you want. Yeah. So yeah, you can have access to the F1 score using the matrix as always. So in a summary, what you use. If you don't care about any difference between the true negative and true positive, like you have pictures of cats and dogs and you don't care about if it's one of or if it's the other, then just you can use the accuracy, that's okay. Also, if you have the same number of both of them, that's okay. If you are missing a true positive for a great risk, that is to say the application of the cancer cell thing, use at least the F1 score. It can be a good choice. Okay, so yes, as I told you, in medicine we usually use precision and F1 score to measure the analysis of prognostic performance. So let's use them. Let's import all of them from scikit-learn.matrix. Matrix import accuracy score. Okay, oops, sorry. A big copy paste here. The precision score, the recall score, and the F1 score. Okay. So now we are at the end of our workshop. We have good models. We think we have the good models, and we just have the final assessment of what are the performance. So here we are going to use the test dataset that we split at the very beginning of the workshop. So let's do it. Okay. So we are going to create a classifier, which is a random forest classifier. The number of estimators is going to be 50. We are going to fit it, fit the features with the labels, okay, and we are going to print everything. So we are going to print basically all these guys here. I'm going to do it quickly. Okay, so we are going to put all those guys here. print, and here we're going to apply them to the features. To the labels tests, and here it will be the prediction made on the features that are in the testing dataset. So CLF dot test to predict with the features tests. Okay. And print everything. I'm just going to increase it a bit here. Okay, so I'm just checking that everything is correct. Okay, so let's do for that. Oh, I forgot. Yeah, that's correct. And it's estimator, not NB. Okay. So it has 95% of accuracy, around 95% of precision, 93% of recall, and 94% of score. Of course, all those guys seems to be a little bit the same, but it seems on our dataset we have as many red dots and blue squares, or the other way around, I don't remember. It seems we have as many as the two. It tends to be a little the same. If we have just like 95% of red square, then the indices will be very different. Okay, so that was for the random forest classifier. Let's do the same for the SVC with the best parameter we estimated. So the support vector classifier with here C to be 1 and gamma to be 1. The comma here. Okay. So it seems that the SVC, the support vector classifier, seems to be slightly above the others. Okay. So basically is what we had for today. Thank you, and I will see you tomorrow.